Good afternoon and welcome everybody to this fifth lecture of the PAVINARI series. This lecture series is conducted by a Gender in Physics Working Group of IPA. The Gender in Physics Working Group, more popularly known as GIPWG, was set up under Indian Physics Association in 2017. The aim is to promote gender equity in physics profession in India. The group has been actively working in promoting the awareness on gender issues and understanding discipline-specific issues, as well as liaisons with similar national and international groups. A first national conference dealing with gender in physics issues was organized in 2019 at University of Hyderabad, and deliberations culminated into the Hyderabad Charter, which has received more than 500 endorsements. The GIPWG, IPA and TIFR will be co-organizing IUPAP-supported international conference on women in physics in July 2023. On the eve of EQUIP, the lecture series PAVINARI is started with an aim to cherish the creditable work of women physicists, sometimes not so well known. PAVINARI stands for Padartha Vigyan Ki Nariya, that is women in physics. Today is the fifth lecture in this series. Previous lectures are also available in the YouTube. Today's lecture is on Agnes Pockels, not so well-known physicist, and her inspiring story will be told by Professor Arnab Bhattacharya. Professor Arnab Bhattacharya is a scientist and science communicator at TIFR, where he leads a research group in semiconductor optoelectronics. He is also presently the center director of TIFR's Homi Bhabha Center for Science Education. Beyond the research lab, Arnab is passionate about science outreach, enjoys talking about science and demonstrating science experiments to all audiences, particularly school college students, and developing low-cost science experiments. Arnab pioneered Chai and Wai, Mumbai's popular science cafe, and is presently the chair of science popularization and public outreach at TIFR. Arnab received 2010 Homi Bhabha Award in Science Education, the 2012 Chevening Rolls-Royce Fellowship for Science and Innovative Leadership, and 2017, he received INSA Indira Gandhi Prize for Popularization of Science. So without further delay, over to Arnab for story on Agnes Pockels.
Thank you, Vandana, for the introduction. And let me just get this thing started off on Zoom. So just to tell you that we are on live on Zoom, but we are also doing this at the Homi Bhabha Center for Science Education, where we have the orientation camp for the physics Olympiad going on. So we have a whole bunch of physics students here and a lot of local people from HBCSE who have come to gathered here to give the talk. So first, in-person audience, apologies. I'm going to sit and give it because I need to be visible on Zoom. Thanks to the lectures going on, we didn't put the tripod in the middle, so you'll have to bear with me over here. And let me just get the screen shared. There we go. Okay, so can you see my screen, online audience? And please ensure to put your questions in the chat. Somebody will read them out. I cannot monitor the chat and see the screen at the same time. Maybe I can try doing it on another computer. Wait, let me see.
I don't know, it's okay. I will take a look at, I'll keep an eye on chat.
Okay, and also on YouTube. So yeah, so today we have come here to discuss the life and work of Agnes Pockels, one of the most amazing women in science, who sort of single-handedly, did the work that gave us what we know as surface science, the field of surface science. And before I tell you her story, let me first make a disclaimer saying that I am not a person who works in surface physics or on monolayer films or anything related to this. I am just a person who likes to tell stories about science. And when Vandana asked me to take up this particular story, I was actually a bit hesitant, but then it was really, I'm glad I did it. It's such a wonderful story. And I must thank the various resources that I have used for this right away, starting from Wikipedia to most of the societies, the American Physical Society, the German Society of Chemists, the Journal of Chemical Education. A lot of them have got very nice articles covering her life and work. There are archival records at the Technical University of Braunschweig, where she actually was based for a while, and also Christian Helm's work at the University of Greifswald. And while I have not been able to put exact image resources for each of the images you'll see on the slides, they're mostly all from public resources or from papers and used in the spirit of academic fair use. Of course, before I start, I must tell you a little knowledge is a dangerous thing. So with that caveat, let's go on for a rather amazing story. So one of the summaries in these books says that she was a self-taught woman who learned from her brother's books and studied the surface tension of liquids while washing dishes. Now that's something intriguing. So while we look at the journey of Agnes Pockels, any story of science is a story of the people who do it. So there'll be a lot of different actors. Some you will know, some are super famous, some not so famous, and we will look at the thing. But always remember that the times in which this work is done is very different from today. The circumstances are different, and it's going to be interesting to see how we look at it with today's lens at the events that happened 100 years ago. So first, in case there are people, this is for a public audience, I don't know who's watching. In case you don't know about surface tension, this is a phenomena that any liquid, if you keep it at rest, tries to become as small as possible to minimize its surface area. This is a property of the liquid and the vapor. And this is the reason why you have, beautiful dewdrops on leaves in the morning. You have ability of insects to just hop over water. You can float a razor blade or a gem clip on water. And this is also all about how we wash things, whether you wash your hands or whether you wash your clothes. If you see on the drop of water, it's not going through the cloth because of surface tension. The moment you add some soap, it reduces the surface tension, allowing the water to penetrate the fabric, interact with the oils and the dirt in it. And that's how all washing. So all washing is about controlling surface tension. You must have heard this phrase called pouring oil on troubled waters, which means you've done something to, diffuse a tense situation or something. Now, the fact that if you pour oil on water, you can generally make the surface calm has been known since antiquity. Okay, the Babylonians knew it. They've written in their stone tablets about it. I think every civilization knew it. And the Roman philosopher Pliny, he wrote that divers and fishermen were used to this, and they added a few drops of oil on the water. It made the surface smooth, and they could see what was there below. Now, for many years, this is a story that's been told. Benjamin Franklin, he wanted to actually try this out, check it out. And once when he was visiting London, he did an experiment in a pond in a place called Clapham Commons over there. And he obviously published a paper in 1774. And this is now the basis for something which, is almost a school experiment. The pictures I'm showing you are from a Royal Society of Chemistry education thing for schools, where people go and throw some oil somewhere and see what happens to it. Here is a picture of oil on Clapham Commons pond. As you can see on the left, there is a turbulent picture of the water, and then it's much calmer after a little bit of oil is added. It's flat. However, these are all observations. If you want to advance science, you need to make measurements, and there are no quantitative measurements of surface tension till we come to Agnes Pockels. Okay. So let's start at the very beginning about her story. So Captain Theodor Pockels, originally he's from North Germany. He is in the Austrian army. And he's posted in Venice, Italy. In those days, the Austro-Hungarian Empire, very large. He's posted in Venice, Italy. And his daughter Agnes Wilhelmine Louisa Pockels is born in Venice, in Italy, in 1862. A few years later, her brother Friedrich Karl Albin Pockels is also born in Italy. However, this is a period where the north of Italy is actually not a very healthy place. There are too many mosquitoes and too much malaria. Okay, so Captain Pockels, he takes early retirement. He retires in 1871 and he goes back to his hometown, which is Braunschweig or Brunswick in English, in Germany. Okay, so where is Braunschweig or Brunswick? And that's their house. What you see is a picture of Captain Pockels and their family house. So Braunschweig or Brunswick is in the north of Germany. It's what you see circled on the map. It's near Hanover, and it's a city which is it's sort of a trading town initially, and it's very famous because the Germans are, of course, very crazy about football, and the rules of football were first described there. That's what you see over here, Fußball. And of course, today in the world of science in Germany, it's very well known. It's the headquarters of what is called the PTB, the national standards agencies for measurement. The Physikalisches Technisches Bundesanstalt, the place where they make all the standard measurements, is headquartered in Braunschweig. Okay, so that's the place where they are. And in the early days, Agnes goes to the municipal high school for girls for 5 years. And unfortunately, in those days, there is no degree available for girls. The only thing you had was 2 natural science classes per week in the final 2 years of high school. That's the only introduction to science that you had. And she says in her autobiographical notes much later that I had a passionate interest in natural sciences, especially physics, and I would have liked to study. But she doesn't have the opportunity to study. And hence, after she finishes her minimum that school thing, she goes back home and is basically trying to take care of her parents. That's what her main thing was, to take care of her parents who are not doing very well. However, her brother could study. So let's get the story of Fritz Pockels. Now, his name is, you'll see both Friedrich and Fritz. Now, in Germany, all Friedrichs are called Fritz in short. That's the sort of, informal name. So Fritz and Friedrich are the same person. So he enters what is the technical high school or Technische Hochschule. Today it's the University of Braunschweig, where he is going to study physics. And thanks to him, at home, he gives Agnes all his physics and mathematics books, and she pretty much learns everything on her own. Apart from textbooks, what is also very important, as you will see in a bit, is he has access to scientific magazines, in particular the magazine called Naturwissenschaftliche Rundschau, which is the Natural Sciences Roundup, which is something like a Physics Today or a Scientific American or something of that sort, a popular magazine of science. And that is going to be very critical in the story, as you'll see in a bit. So she is now reading at home, thanks to the books provided by her brother, thanks to the magazines, scientific literature that is being brought home, and she's learning on her own. Let's take a little bit look at her brother. Okay. So Friedrich Pockels eventually moves from Braunschweig to the big university nearby, which is Göttingen, and he goes to the this is the center of physics at the just in the 1880s, and he gets his PhD from there. And then he decides he's going to be an academic, and he gets a position as a professor of theoretical physics at the other big university in Germany, which is the University of Heidelberg. Okay, and his topic of interest, his research topic, is electro-optics. In particular, how does refractive index change due to an electric field? Okay, now you may have heard of, if you're physics students or if you've done some physics, you may have heard of the Pockels effect. And this Pockels electro-optical effect is named after not Agnes Pockels, but her brother Fritz Pockels, or Friedrich Pockels. Okay, this is a linear electro-optic effect. That means the refractive index of a medium varies linearly with an electric field, and this is seen in crystals which do not have a center of symmetry. So crystals like potassium hydrogen phosphate, which is KDP, or beta barium borate, or lithium niobate, these are very important crystals in the world of nonlinear optics today. And these crystals help us make what is called a Pockels cell. And this is important for making quarter wave plates, anything dealing with changing the properties of polarized light. If you want to make a switch for polarized light, if you want a shutter, a fast shutter, or something called a Q switch used in a laser, all these things use a Pockels cell depending on the Pockels effect after Friedrich Pockels. Now, there is also another effect which is called the Kerr effect. The Kerr effect is another nonlinearity. Please remember that's a quadratic nonlinearity. It's the change in refractive index depending on the square of the electric field. Okay, so there are also Kerr cells and things like this. Kerr is a Scottish scientist. So these are two very different effects, but very useful effects today. Okay, so on that note, so her brother is someone who has made a name for himself in physics. What is happening at home? At home, this is what she says. These are reports by her sister-in-law, the wife of Fritz Pockels. She wrote a very long sort of memoir on Agnes Pockels' life. And she says that her studies were often conducted in the kitchen, where Agnes, being the daughter of the household, had to do her chores, and where it was always nice and warm. In this way, Agnes conducted her first observations in the field of surface science. This is really true, no joke or poetic license. what millions of women see every day without pleasure and are anxious to get rid of, i.e. the greasy washing up water. Encourage this girl to make observations and eventually do scientific investigations. So washing dishes actually gives her the idea that she can make some measurements in surface science. Now, what is the scene at home? This is a picture of her diary that she maintains. And she says, well, in 1877, mummy's nerve trouble, 1881, she's ill in bed, winter, daddy has something, daddy has cataract, daddy is ill in March, Fritz has influenza. You know, the family suffered with much illness. And even this took a toll on the health of Agnes. And some years she herself had to be in a sanatorium later, and her science had to take second place. And when she was told that she needs to take care of herself and her own health, she used to say, like a soldier, I stand firm at my post, caring for my aged parents. So she was determined that she would fulfill her duties to her family, take care of her parents, and do the science on the side. What did she do? Well, she made a simple gadget that allowed her to measure things. Measure things means measure surface tension. And the thing she built, she called it the Schieberine, which is a shift trough, where you can keep some water and shift something. And she has entries in her diary saying, I have discovered the abnormal behavior of the water surface. I've developed this. I've made a larger size version of this. So she's actually very meticulous in making her observations. Okay. And what is this thing? What does it have? It is a rectangular trough, 70 centimeters long, 5 centimeters wide, 2 centimeters high. It's filled with water to the top of it. And there is another strip of tin at the side, which you can move across this water surface. Okay. The underside of this tin strip is always touching the water and you can move it. Hence, if you put oil on one side, you can shift the area by moving the strip. You can shift the area of the oil film. And she has a remarkable way of measuring the surface tension. She has a very simple balance, the balance that, pan wala balance. And she uses a button. She uses a button, just a button from the cloth, from the dress, a 6 millimeter diameter button. The button is touching the water. It's tied over a pulley to this little pan. She will put weights over there and see at what weight will the button lift from the water. Because the surface tension will try and hold it in. When you put some weights, it will lift off, and hence she can now quantify surface tension. This is a picture of the trough, which is rebuilt at the Technical University. Unfortunately, she is taking measurements over a 10-year period. Meticulous measurement. She doesn't have any interaction with other scientists. She doesn't know what's going on. She sent her results to the professors of physics, where at the University of Göttingen, her brother was there. They are not interested. They are not interested. Nobody's interested in the work of somebody who's working at home. Finally, remember that magazine that her brother has got, Naturwissenschaftliches Rundschau. Okay. She reads about the work of Raleigh in that magazine. That Raleigh is also interested in working on surfaces. So enter the next actor in our story. That's John William Strutt. That's his name. He was a 3rd Baron or Lord Raleigh. That's what he named. And his guys are clearly a very, very versatile scientist. You definitely have heard of him. He got his Nobel Prize in physics for discovering argon. But there are a huge list of other things he has done. There's Rayleigh scattering that tells you why the sky is blue and all that. The Rayleigh criterion for various things, Rayleigh-Ritz method of solving eigenvalues, dissipation in fluids, Rayleigh-Taylor instabilities, Rayleigh-Jeans law, the UV catastrophe and all that, the Rayleigh number in fluid flow, instabilities, lots of, he has done work in many, many fields of physics and has contributed immensely to all of them. So he's this very famous scientist in the UK, fellow of the Royal Society, Nobel Prize, whatever. Of course, he had not got his Nobel Prize at that time, but famous scientist who's working on surfaces. What's he interested in? Rayleigh is interested in water surfaces. And of course, he has a lab. He's not working at home. He has a proper lab. He's got some proper equipment. It's called the oscillating needle equipment. And he is also looking at what happens to surface tension. For example, he knows that if you add soap or camphor, etc., that the surface tension goes down. If you add contamination, and there's a sense of, a dirty finger or grease or oil, things go up. Then he's creating waves on a surface by using a fan and then seeing what happens if you put a drop of oil. This fan is making the surface turbulent, but then the oil sort of calms it down. Then he sees how powdered sulfur disperses on water. So he's making experiments in surface, things putting on the surface of water, published in the Proceedings of the Royal Society of London. But also, I mean, he's a famous guy, so the magazines write about the work he's doing, and this is read by Agnes Pockels. Now, she decides, look, the guys in Germany are not listening to me. Let me write to Raleigh. So she takes the courage to write a letter, a 12-page letter in German, detailing everything she has done, and sends it to something. Now, today, if you say, dear Lord, you'd think, oh God, something is wrong. That's the only time you use some expression like dear Lord. But here she actually says, Herr Lord, I mean, dear Lord, basically. Raleigh recognizes the value of this work and says that this is something really interesting. And he uses his stature to write to Nature and say that this is great work. It should be published. So this leads to the first Nature paper. This is 10 years of work in one short letter to the editor. And this letter to the editor over here, it says that I shall be obliged if you can find space for the accompanying translation of an interesting letter which I have received from a German lady who, with very homely appliances. By the way, the good thing about Nature, it's all digital right now. So you don't have to struggle to read this fine thing. You can go to Nature and search for it, and you will get it in a much more readable format. So it says that I shall be obliged if you can find some space for the accompanying translation of an interesting letter which I have received from a German lady who, with very homely appliances, has arrived at valuable results respecting the behavior of contaminated water surfaces. The earlier part of Miss Pockels' letter covers nearly the same ground as some of my own recent work, and in the main harmonizes with it. The latter section seems very suggestive, raising, if they not fully answer, some very important questions. I hope to soon find the opportunity of repeating some of Miss Pockels' experiments. So this is her first Nature paper, and she says in that paper that I will now put together the most important results obtained with this apparatus, most of which, though perhaps not all, are known to you. She's writing to Raleigh. And they just take that paper, translate it, and put it in. They don't, and she goes like 1, behavior of the surface tension, 2, mobility, 3, this. So she just enumerates this point observation that she has made and sends it. And in summary, what are these observations? Is this. 1, the surface tension of a contaminated water surface varies if its surface is compressed or expanded. That is, if I have some oil on water in this thing, if I move that little slider that I have and increase the surface area or decrease the surface area, the surface tension changes. On compression, the surface tension decreases by a factor of 2. On expansion, it increases till some value is reached, and then it remains a constant. So the water surface can exist in 2 states. One in which the surface tension is constant, even though the size changes. And the other one, if you change the size, it leads to the change in surface tension. The cleaner the surface, the more you can compress it. You can remove the surface layer by putting a piece of paper and taking it off, and then it cleans it out, sort of. This wave damping, which is the fact that things get calm when you add the oil, is pronounced. The lower the surface tension, the more pronounced it is. All solid bodies, no matter how clean, will contaminate a water surface that is in the normal state. Solid materials like glass or metals increase the contamination. Camphor or flour will reduce the surface tension. Then if you have a contamination with different substances, it causes some material current. Things are flowing around. Then she talks a little bit about solutions of sugar. Sugar has a higher surface tension, yet if you put a piece of sugar locally somewhere, it will change. So from these experiments, I concluded that the surface layer, takes up soluble stuff, etc., etc. So she makes these observations. Just silence the phone, please. Yeah. So these are these observations, and this leads essentially to the field of surface science taking off. This paper is the one place where you start with quantitative measurements of surface tension and many of the key observations of thin films on water, which will get refined with time. But this is the beginning, and this is where the field of surface science begins, thanks to the work of Agnes Pockels. And just remember that she is gets an idea from, oil films on water when you're washing dishes. But oil films on water over the last 50 or 100 years have been central to so many issues in chemistry and biology. Just think of lipid bilayers. Lipid bilayers are what make our cells. There is so much work that has gone into it. And we have been able to pull these layers of surfaces, etc., because of the techniques developed by the work of Agnes Pockels. Okay. Any immediate questions so far, Vandana? Anything to be, any comments? Go on.
No. Go on. Yeah.
Okay.
Yeah.
All right. So now, just take a minute and think. These are the times where luck is so critical. Just imagine she writes to Raleigh and Raleigh had ignored that letter. Just imagine Ramanujan had written to Hardy, Hardy had ignored that letter. Right? There are times where it is just important that things happen at the right time. This is a case where it's been extremely lucky that Raleigh took it seriously and decided to follow up on it, and the world knows about this work. She made a lot of other observations as well, eventually, that if you clean glass, you can clean glass, the surface, by heating it in a flame and then putting it in the water. If the glass is clean, things don't move around, no material current happens. If you want to make a good equipment, the material of the trough and the barrier, you need very high contact angles with water. And then she studied different oils. Some oils have a very flat layer with the same, you'll get colors due to interference. They'll be constant. They will, how they thin out, how they break. And then she optimized some other method, which is a paper in Science in 1926. So there are lots of other observations she made in this field. Now, there is another very important thing. She came up with this concept of what is today called compression isotherms. Okay. Now, if you are changing the surface, what you're doing is you're observing how the surface tension on the film changes as the film area changes. When you have these, molecules which are mostly what are called amphiphilic, that is, one end likes water, one end doesn't like water, soap molecules. So what happens, and today we know that this is these molecules have some long organic chain which doesn't like water, and the head which likes water. So the heads are in the water. If it's very dilute, if it's spread out, it's almost like a gas. They're not talking to each other. As you reduce the area, you will sort of bring them closer. They behave like a liquid. Eventually they all touch each other. You have a monolayer film. That's when they behave like a solid. So if you plot, and what you see on the left side is her data, where she has there is some different surfactants, there is different soaps and something else. They all go to this point. And today this point is called the Pockels point. Okay, where the surface tension changes with the area of the film. And all these things allowed her to determine, okay, so when all this thing comes together, it means there is now just a monolayer of it without any gaps. And that she could allowed us to calculate what is the area occupied by a single molecule. And she estimated to be of the order of 20 angstrom squared. Okay, so this is the Pockels point, and the idea of these are the first compression isotherms that have been measured in surface science. Now, another great is going to enter the field. This great is Irving Langmuir. Irving Langmuir is an American who is, has done, fantastic work in pretty much every field he has touched: physics, chemistry, engineering, whatever else. His Nobel Prize is in chemistry. In 1932, he gets the Nobel Prize in chemistry for surface chemistry. And a lot of his work for that Nobel Prize is thanks to the influence of Agnes Pockels. Okay, but Langmuir, of course, is a person who has a legacy in whatever he has done. There is Langmuir's work on atomic structure with Jane Lewis and things like this. He started work on bulbs, gas-filled lamps. In fact, if you've looked at an old bulb, today you have LED lamps. If you look at an old bulb, it has a tungsten filament which is coiled. The idea of making a coiled filament is his. Okay, he introduced the thing about hydrogen welding. He worked in plasma physics. So there are Langmuir waves. There's a Langmuir probe you use to measure the electron density in a plasma. He worked on ocean currents. I mean, whatever he did, he's got something in it. Okay. And he did a lot of work on oil films on water and on surface science. In fact, one of the most important journals in surface science in chemistry is called Langmuir. It's the name of the journal. Okay. So Langmuir, by the way, what's probably not known to many is he has a bachelor's in metallurgical engineering from the Columbia School of Mines. And then if you wanted to do physics in the early part of the 20th century, where would you go? Germany. So Langmuir did his PhD in Göttingen, and he worked with another great of physics, Walther Nernst, okay, thermodynamic guy, Nernst equilibrium. Nernst was also working on lamps. And this is just to show you that Nernst had a very different idea. One of the biggest problems of the early bulbs was they needed vacuum. Vacuum technology was not yet developed so much. The problem was, how do you evacuate it? Right? Langmuir's solution later on was, we'll fill it with argon, we will not have a vacuum. Okay. But this guy said, no, let's not use a metal. Let's use an oxide and heat it up and make it glow. So they were making these Nernst heaters, which is that picture you see on your screen over here, or it's on that side, I guess, in the hall. This is the Nernst lamp. And this was a glow bar like thing. He worked on it. When he went back to the US, Langmuir was hired by the General Electric's GE research in Schenectady. And he pretty much stayed there most of his life in an industrial research environment. But he did a lot of basic research over there. Now, since he was in Göttingen, it is possible that Irving Langmuir already knew about the work of Agnes Pockels, because it's the physics department, brothers there, whatever else. But he certainly followed up with it once he went back and started his work on oil films. Okay. So then Langmuir publishes a very classic paper. This is a paper in JACS, the Journal of the American Chemical Society, in 1917, which is essentially, this is a 52-page paper, which is essentially covers everything they've given him as Nobel Prize. Okay. This is it's called the properties of solids and liquids, and these are liquids. And one section of the paper is on oil films on water. And of course, he says that, his reference one is it's an overview article. And then reference 2 is Miss A. Pockels' work. And she showed that very small amounts of oil on the surface have no appreciable effect on the surface tension, but that surface tension begins to decrease suddenly when the oil per unit area is increased beyond a limit, etc., etc. Raleigh repeated this and find out. So he knows about her work. He cites her work, and he decides to improve the setup that Agnes Pockels has made. Okay. And to cut a long story short, today, the standard thing to work on thin films of materials like soap films, oil films, etc., on water is called, these films are called Langmuir-Blodgett or Langmuir-Blodgett films. I think it's Blodgett. And this apparatus is called the Langmuir-Blodgett trough. Okay. He continues the study of Agnes Pockels. He builds more sophisticated versions of this to study the properties of monolayers. And this is the sort of the current design of the trough, where you have it's vibration isolated, so you can get a very stable surface. You can move it very carefully in a motorized manner. You can dip something and pull it out at a constant rate. So lots of improvements on it. This is the standard technique used in the lab to prepare monolayers, change the density of monolayers, to be able to dip something else and transfer these layers to a different substrate. This is the Langmuir-Blodgett films and the Langmuir-Blodgett trough apparatus. I think if you've been in physics, at least beyond a certain level, you would have heard about LB films and LB troughs. The question is, who is the Blodgett in this part? And most people don't know this. Langmuir, of course, is super famous. Who is Blodgett? And it turns out, and I didn't know this myself, is another remarkable woman, unheard of in science, Catherine Burr Blodgett. And there is a good reason I'm giving you the full name. You'll see in the next slide, who has an equally interesting story. Catherine Blodgett, I think it's Blodgett and not Blodgett, though that's what many people call it, even in the US, simply because what happens is her father is a patent attorney in GE, in the labs in Schenectady. Unfortunately, her father gets shot in some typical US stuff. Somebody gets shot just before she is born. But the father happens to be a friend of Irving Langmuir. And after this, her mother takes her to France in her early childhood. So given that she went to France, my feeling is it's Blodgett and a typical French name, things like this. But anyway, so after some time, they come back to the US. Langmuir knows the family well. Langmuir gives Catherine Blodgett a tour of the GE labs and says, look, you should do research. If you do research, I'll give you a job. Okay. But by the way, if you want a job here, you have to study. And you're going to get a master's at least. So fine. She's interested. She gets a master's in physics from the University of Chicago and joins the lab. After some time, she decides she wants to do a PhD. So she moves to the University of Cambridge in the UK, and she's the first woman to get a PhD in physics from Cambridge. And obviously, she's the first woman PhD employee in GE research. She had joined it anyway before that. And it is her inputs. She is the one who actually did most of the hard work in designing this Langmuir-Blodgett curve. Langmuir was a famous scientist. He's like the manager of the lab doing lots of things. She was the main person who designed the Langmuir-Blodgett curve. Is there a question? No. Okay. Now, the other critical thing she did was to go beyond monolayers. Okay. People, you can take a monolayer and lift it off. But can you do this multiple times? Can you dip a monolayer, take it off, get one more monolayer on it, get one more monolayer, and build up thin films? And in particular, she was working with a material called barium stearate. And barium stearate is very useful. She used it. She found that at a certain critical thickness, you could use this to make a anti-reflective coating on glass. So basically lambda/4 kind of a coating where for a certain wavelength, the reflected wave from the back and it just cancels out. So it's an anti-reflective coating. Okay. Remember, G is an industrial research lab. They want to use it somewhere. And the first place they really used it in the public, that public came to know that there are anti-reflective coatings available on glass, was in movie shooting equipment that is used in Hollywood to make a film. It's a very famous film called Gone with the Wind. Gone with the Wind in 1939 is the first film that uses anti-reflecting coatings in the optics for their various things. People are amazed at the clarity of the movie, etc., etc. And obviously, just like if you have Bollywood marketing for you in here, in those days, if your product was using it there, suddenly anti-reflecting coatings of GE became extremely popular, and they could sort of make a product out of it. Okay. Of course, during the war, she's in industrial research, so she was assigned to many other projects, right, ranging from airplane de-icing to figuring out better compositions of gas masks, which is also depending on surface science. So she did a lot of things. This is Catherine Blodgett of the Langmuir-Blodgett films. Yes, there's a question here locally. Let me just take that. Yes.
What is airplane de-icing?
What is airplane de-icing? So if you're in a very cold climate, if you do nothing and you have airplane wings, if the humidity is very high, ice forms on them. Okay, and that could be dangerous because the weight of the wings will go down and it can interfere with the flight. So in cold countries, what they do is before a plane takes off, they spray a de-icer on it, something that prevents ice condensation on the wings. That's the airplane de-icing. Okay, so that was an aside. I'm going to take an aside of an aside because there is another Catherine Blodgett. This is Catherine Blodgett-Jebby. Okay, she is a niece and namesake of Catherine Blodgett. She's named after this Catherine Blodgett, who is and she is a very different person. Also a physicist, but an astrophysicist who worked on hot stellar atmospheres. Okay, in atmosphere of stars. And after she had finished her PhD, she joined what was the National Bureau of Standards, and they had a lab looking at laboratory astrophysics. This lab eventually become something which is GILA in Boulder, Colorado, joint in something for laboratory astrophysics. GILA is now a very famous lab. And out there, she was a founding director and the only director, because eventually these institutes got merged into something else, the Physical Measurement Laboratory and the Center for Atomic, Molecular and Optical Physics. And these are the predecessors of the US NIST, the National Institute of Standards. And this is came out of the two institutes that she was the director of. They got merged. Okay. Now that is, of course, she is a physicist, in administrative roles and leadership roles. That's okay. But the important thing is, as an administrator, she gave a huge support to encourage women for careers in physics. Okay. And what I show you here is the thing given to the US Senate. The record when they renamed the buildings at NIST after her, it said that the most enduring aspect of Dr. Jebby's legacy, however, will be the program she pioneered to support diversity and her tireless efforts to promote the inclusion of women and minorities in so-called STEM fields around the country. And she started an early group for women in physics at the IUPAP, the IUPAP. This group organizes over the years, a conference called the International Conference of Women in Physics. So now an aside of an aside of an aside is some shameless advertising that HBCSE we are hosting the International Conference of Women in Physics in 2023 in July, mid-July. It's an online conference, but it's sort of hosted by us over here in India. India won the bid to host this conference. So this all is in a way strangely connected to the story I've been telling you so far. Okay, let's get back to Agnes Pockels. So she had a lot of other interests, including just translating. She knew German, she knew English, she was reading. So she translated a book about the tides and similar phenomena in the solar system. She translated that into German. This was 1902. And in the later years, because she had this paper in Nature, I mean, this is still happens today. If you have a really high profile paper, it helps you get inroads into the community. She was then able to sort of work at the sort of physics institute of this technical high school or technical university in Braunschweig, and also publish in German journals. In those days, the big physics journals are all German journals. So this Annalen der Physik, in which Einstein published all his key papers. This is the pure sciences or the natural sciences. So she has papers on the anomalies of the water surface. There are experiments on the interface tension, surface tension in using a cohesion balance. So these are different. She publishes a lot of papers in German journals as well. Okay, so it sort of gets her in. However, while she started getting accepted into this physics community in Germany, the times started becoming hard. Her father dies in 1906. Remember, she's extremely committed to taking care of family. Her father dies in 1906. Fritz, her brother, dies in 1913. Her mother dies in 1914. And this is the period when World War I starts. There is huge inflation in Germany, becomes very difficult to do any work, and her activity is slowed down. And at some point, she sort of decides that, okay, I've had enough of doing this active research. I'm going to lead a quiet life. So she became one of the sort of she was called Agnes Auntie in the circles in Braunschweig. She was just there, and she organized a lot of intellectual debates and things like this at her house. But she was just Agnes Auntie. One very important publication that gives information on her life and her work is a special publication, a Festschrift, on her occasion of her 70th birthday by Wilhelm Ostwald. Wilhelm Ostwald is another pioneer of surface physics, chemistry, whatever you call it, Ostwald ripening, things like this. So he was the editor of the Journal of Colloid Zeitschrift, and he publishes this, the work and of Agnes Pockels of interfaces and films. This is in the Colloid Journal. And one very nice thing is, in this, it's not only Ostwald writing about her, but he speaks to her and he has like an interview. And there are a lot of autobiographical passages written by Agnes Pockels herself. And these are very, sort of, it tells you about her as a person, her life, her values. So one of them I've told you earlier already before. I had a passionate interest to study in natural sciences, but I would have liked to study, but basically she couldn't. Then she says that, encouraged by the support of Lord Raleigh and the publication's nature, I dared to submit papers to German journals. Then she says, I learned to my great joy that my work is being used by others for their investigations. She was quite happy. I mean, she was not feeling bad that other people are not giving her credit for what she has done. And then she actually says that when my brother died in 1930, the alarms of war and the post-war period engulfed me, and the Bibletter, this is the Bibletter to the Annalen der Physik, is like a supplementary issue to the Annalen der Physik, ceased publication. I was no longer in a position to obtain the relevant literature, and at the end, I completely lost contact with research in my field, the deterioration in my eyesight and my health altogether also being a contributing factor. So she decides she's going to sort of pull out. However, she does get some late recognition. In 1931, she receives the Laura R. Leonard Prize of the German Colloid Society. I tried like a lot to find who is this Laura R. Leonard, but I just could not. I've just searched a lot, but even in German, but I just could not. And the citation is for her quantitative investigations of the properties of interfaces and surface films, for the methods she used, which have since become fundamental in modern colloidal science. In 1932, the lady who was denied admission, could not go to college, was not allowed to study, was given the first honorary doctorate given to a woman by this time that's become Technische Hochschule, is Technical University. TU Braunschweig gives her an honorary doctorate. That's in 1932. Her health is deteriorating, and eventually she actually passes away in 1935 in Braunschweig itself. And Science magazine carried her obituary, and it says that in a period where ordinary avenues of higher education were hardly accessible to a woman, the lively interest in science which she early developed and forced to seek an outlet in self-education, mainly by the aid of books. And at the age of 19, she made her first important experiment of observation of surface phenomena. And the following year derived a simple means of measuring the relationship between surface tension and surface area, which has become a most important tool in the hands of investigators such as Lord Rayleigh, Irving Langmuir, R. Marcellin, and N.K. Adams, and other people. Okay, so this is her life. And at the end, I will just leave you with one thing to think about, two things. Just imagine what more Agnes Pockels might have achieved if she was given a chance to study and pursue a career of her own. And also, this is one story we are aware of. There are possibly many such people who have historically been denied a chance to study and pursue a career just because of the way society placed restrictions on them. But also on the other side is a more positive view. That is to step back and think that even in the most mundane of situations, washing dishes, right, there can be a treasure trove of science that is hidden. And if you are smart and you can, take it out, there's no end to where you can take it. Thank you very much, and I'm happy to take questions.
Thank you, Arnab, for a very, very interesting talk. It's an amazing, fascinating story, and you also brought out so many different facets and connections with other women in science connected with that. So it's just, that's essentially the purpose of PAVINARI. I'm sure there are many questions. So maybe you take first from the live audience, and then we will go.
Okay, live audience here, are there questions? I will repeat it for the online audience. Yes, please, go ahead.
Now this that you mentioned about her, did she ever have a family? Did she marry? Did she have children? Are there survivors?
Okay, the question is, in all that I've mentioned, anything about her family? Did she have children? Are there survivors? The answer is no. She was committed to caring for her parents, and hence she did not marry. Any other questions here in the room? Yes, no? Okay, we'll give you some time to think. Meanwhile, we can go ahead to online. I can also see if I can turn.
Yeah, so so there's a question from Vivek that did she get any support from her brother?
Yes, I mean, in the sense that I think her brother, and she acknowledges this in many of her writings, that, it's her brother who sort of says that, yes, you should study, and gives her all his books, all his, the science magazines, whatever he can get from the university, he brings home and gives it to her so that she can study. And I think the reason she writes to professors in Göttingen is because her brother is there. But of course, I think her brother can't influence what other people will think about her work. But yes, I think she did receive support from her brother.
No, what I meant was, did she receive any support in terms of, building some equipment and so on? Either financial or material?
I do not know. I mean, there is nothing in what I have read that says that she received any support in terms of building instruments or things like this. We don't know if she discussed it with her brother or not, but nothing in whatever I have picked up, both in the English and the German things that I have read.
Yeah, same thing I would support. There is nothing in the available things that she got any support from her brother in building the equipment. The original turf that she made. Hello?
Yeah, I think the original turf is entirely made by her at home.
Yeah. Thanks, Ulba, for adding that information.
Just can I give one quote from?
Sure.
Oh, yes, of course.
Sure.
Yeah. He said in her honor that she not only taught us cleanliness at work, but also taught us how to measure it.
Yes, that's from Ostwald. Actually, that is the
That
Ostwald
was
says.
Nice, Ostwald said about her.
Ostwald in his fest script ends by saying that she not only taught us cleanliness, but she also taught us how to measure it.
Yeah. And there was, I think in 1987, special issue or some conference on this Langmuir Bloodgate films. And there it was particularly mentioned about Agnes Pockels.
Okay.
It was Thin Solid Films, and that was a journal. It had special issue on these kind of films.
Yeah, there seems to be a very detailed report on her work in a 1970 issue of Chemistry and Industry, but that is, I have not been able to track that thing down. It doesn't seem to be online, and I don't know where one could find it. But I have a reference that I'm really looking for, which I couldn't find before this talk, at least.
Yeah, this one was in Thin Solid Films, a special issue. And I happened to read that for the first time, actually, because of my interest in thin films. And there it was mentioned about Agnes Pockels, and I followed it and tried to write a story about it. Thank you very much. Just
okay. I saw Ajit's hand up.
Ajit has a question.
You may have mentioned it. I may have missed it. It looks unlikely that she would have tried for any position, I guess, is it? Because
she would have
tried for any position, like academic position or something.
No. So after her Nature paper is published and all that, the university sort of grudgingly allows her to enter the physics department and read and do some work there. But she does not have any position at all.
Did she look for it? No, what I'm asking, did she look for a position? I
don't think so, because if you look at the history of citizen scientists, the other thing with that, because she didn't have a degree and didn't have a position, she is considered one of the first citizen scientists. Okay, there are two questions here, so I should take those as well. But so Shikha, I see your hand up, but let me just take these two questions here. So yeah, you were first over there. Go ahead. I'll repeat it. Okay, the question is, how did she calculate that the area of an atom was 20 angstrom squared? I think the exact calculation I don't remember right now, but it goes something like, the amount of oil you have put, that this is, I don't know, olive oil or whatever it is, that it is mostly this molecular weight. So this is the amount of oil you have put. Avogadro tells you there are so many atoms in it. The area it is taking. You assume that the molecules are all just completely covering the surface with no holes, and then you can calculate the approximate average area per molecule. Obviously, knowing that the molecules are not going to be. Remember, what they didn't know is that these things are the alkane chains are going to be standing up and things like this. But that's how approximately she did it. Yeah. So you obviously have some assumptions to make, and one of the assumptions is that when it spreads completely, if you put a very small amount, it's going to be a monolayer. That's an assumption that you make. Under the assumption that it's a monolayer, you can do this.
There's a question from Shikha and then from Vivek.
Yeah, I see Datar, I see Shikha. What was it? One sec. What was the question again? Yeah, it's an approximate calculation, assuming it's a monolayer. It's not an exact calculation. It'll obviously depend on the kind of oil you put and how big the molecule is and things like this. It's one of the first estimations.
It's an estimate, not a calculation.
It's an estimate. It's not an exact calculation of it. It's an estimate. Yeah. But even in those days, to figure out what is the size of a molecule or something is itself an interesting number that you can get, right?
Yeah. Okay, Shikha.
Okay, let me get one question from there. Yes, Shikha, go ahead.
Okay, so what I wanted to ask this Langmuir paper in 1917, on which this Nobel Prize is based. So how much is it documented that it is like a Miss Nobel Prize for Agnes Pockels, or most of the work is from her work?
So, let me say this, though the 1917 paper of Langmuir, starts off by, in the section on oil films, on water, starts off by acknowledging Agnes Pockels' work. There is a lot of other stuff in the paper as well, which is way beyond whatever Agnes Pockels has done. Now, he does not refer to her at all in his Nobel lecture, which I also went through, just to check, did he refer to her in the Nobel lecture? And if you look at the sort of overall, what he covers in the Nobel lecture and what is covered in both part 1 and part 2 of the two papers, the oil and water part is admittedly not the sort of highlight of it. It's an important part. The design of this Prof obviously is inspired by Pockels' work, which he of course acknowledges, but I don't know. I mean, in that way, I would say that probably Catherine Roger is a far more higher in the, should have been maybe given the Nobel along with him rather than Agnes Pockels actually. I mean, though, yeah, 3 people can get it, but, I mean, that paper has a lot more than just this oil and water part.
Yeah, thank you for very nice talk. Really motivating and tells us about so many other characters who are part of this story. Yes. Okay. Thank you.
Okay, great. Thanks, Shikha. Vivek, before that, can I take a question from the local audience here?
Yeah,
Okay,
sure.
Okay, yeah, go ahead, please.
Sir, can you please explain?
Okay, the question is, how do you test the cleanliness of a surface?
Very good question.
Discover the effects of
Okay, let me ask you, what kind of surfaces? I mean, you ask me about semiconductor surfaces, I can give you an answer, but are you talking about a water surface?
Yes, I mean, what is it?
Or a fluid surface? Well, honestly, I will say that I really don't know, but what she was testing is, if I am putting a glass rod in, I can check if the glass rod is clean or not. If I heat up the glass rod in a fire and clean it, if I put it in, there is no change. Whereas if it was dirty and I put it in, there would be a change in surface tension. So surface tension, the change in surface tension is what she used as a metric for contamination. Okay. Does that sort of give you a clue? Yeah. But I mean, I think it's a very difficult question to answer. How do you say that a surface is clean? If it's a semiconductor surface, I can tell you can look at the electron diffraction from it and see how regular it is or something. But I don't know about water surfaces. Okay, Vivek. Yeah, go ahead.
No, so I just typed the question. So basically, it's a slightly side question. How accurately can one compute the surface tension of different interfaces?
I don't see your question. What is the question?
It was sent only to me, so that's why you don't see. So
okay.
Sorry. I continued.
He's saying anyway, he can repeat the
I
question.
can repeat it. How accurately can one compute surface tension and compare it with, let's say, experiment of
how accurately can one compute the surface tension?
Various interfaces.
I mean, honestly, again, I don't know, but just going by a gut feeling today, that if you can do molecular dynamics simulations, I am sure that, I mean, after all, you're looking at the forces between molecules. In the bulk, they are going to be isotropic. On the surface, there's some component in and a tangential component. The tangential component is what we call surface tension. So I think you can probably compute it for a given vapor liquid interface. But I don't know. I mean, maybe we should ask some of our computational chemistry people.
Or maybe vapor and liquid is probably simpler than a liquid-liquid interface.
Yeah, I mean, I guess there are some approximations you can make in vapor liquid, which you can't do in liquid. But I think we should ask this to our computational chemistry people. They probably know better on how these things are done. I really don't.
Yeah. I don't see any more questions on Zoom.
Any other questions here?
No, not in the YouTube.
Wait, there's another one here. Yeah, go ahead.
Sure.
Hey guys, let him ask this question. No, just hang on.
Like how to we are sliding it's such that communicator voltage, how to basically build something.
So I mean, there's no feed. So how do you know that you've got something? What she was doing is sliding it and measuring the surface tension and seeing if the surface tension value went up and saturated to a point. And then you know that at that point something has happened, that all molecules have arranged. So that is, I mean, you can't, I don't think you can see it as such at this very dilute things. Maybe for some molecules, there are some interference effects you can see, but I think that it would be mostly by just measuring the surface tension and seeing how it behaved with area that you can, then plot it and see what happens. Okay, I think there are no more in-house questions here, I see.
So I just want to make a comment. We heard the previous talk was on Lisa Meitner, and we also see certain similarities which are there in the life. But, Agnes Pockels' life was somewhat very hard because she really struggled to get a recognition. But it's very heartening to see that she was given a degree. And as you say, the positive to take home is that you can find the treasure of the science in any situation if you look deep enough. So that's something really very inspiring and nice. Yeah. So I take this opportunity to thank Arnab for really a very, very interesting talk and covering a large canvas. And thanks to Homi Science Center for organizing this talk, hosting this talk. So we thank all the audience present, the Olympiad students who are present there at HBCSE. Wishing them all the best, and also all online audience.
All right, all the best to you students over here from the organizers of the thing. And
next lecture will be by Shikha on Rosalind Franklin. It will be announced shortly. So we look forward to seeing you again there in May. Okay, thank you very much. Bye.